to take a break, this is it. So let's take 5, come back at 40 after. All right, folks. So here we go. We're gonna keep going now. So it turns out, just like we had a chi-squared goodness of fit test for like a singular list of numbers, there is a chi-square test that we apply to two-way tables. Okay, and when we think about how we calculate that value for chi-squared was equal to the sum of our observed minus our expected squared over our expected. The observed counts are really easy to find in a two-way table because I give you what I give you in the two-way table is the observed count. Is everybody good? Okay. Like if I were to say, what is the observed count of people who listen to jazz that completed the assignment? Right now, could you tell me that? Yeah, 23 people did. The question becomes, what is our expected count? And when we talk about expected, we're basically assuming we're going to calculate that expected if the two variables are independent. Okay? Is everybody good? All right. So we did this on the previous page. The probability that someone completed the assignment was 80 out of 150, which worked out to be 0.533. Now, what does that mean? It means overall, 53.3% of the students in this experiment were going to complete the assignment. And if the two events were independent, we would expect 53% of each category to have listened to complete the assignment, right? If the different kinds of music don't matter to whether you're going to complete the assignment, that 53% should have applied to every single group. Is everybody good? So in some respects, if I wanted to find if the two events are independent, what would I expect to be the completions for the jazz group? I would take that 0.533 times the number of kids who listen to jazz music.
24.
Is it exactly 24?
Yeah, if you use like the exact value.
Now, is everybody with me that in reality, I'm going to cross out that 0.533 for a second. In reality, if I wanted to write down all the numbers that really got me there, it would be 80 times 45 over 150. And then for the next one, it would be 80 over 150 times. So this was jazz. For classical,
28.8.
and for the non, it would be 80 over 150 times 51. Now, I want to go back one more time. And what I'm going to do is I'm going to highlight these numbers. Ready? So this was the expected count for the jazz group. 80, 150, 45. And then if I did, the only difference is if I'm doing the exact same thing for classical, 80, 150, 54. Everybody seeing it? So what's really going on here? If I want to find it for this cell, I'm going to take my row total times my column total over my table total. Okay? So to calculate expected counts on a two-way table, we do the row total times the column total on top. On bottom is the table total. And when we do these, all of those numbers came from assume independence. Now, really important idea. If I'm making those expected counts assuming the two events are independent, that tells me that my null hypothesis will be independent. So it'll be more formal than this. But remember Remember, our logic of a test is we assume our null hypothesis is true. We did this with the goodness of fit. We assumed each of our proportions were correct. So our expected counts are our assumption, are our null hypothesis. It's what we would expect if the null hypothesis is true. And if our chi-squared value is weird enough, it's unlikely enough to get that chi-squared value, we can assume our null hypothesis is incorrect, reject it, and conclude the alternative. Okay. So, what typically with a more so with a two-way table than with a goodness of fit test, what I like to do is put my expected counts in parentheses in my table. So we had 24, 28.8, 27.2. So if I wanted to find the expected count for this circled cell here, the jazz not completed, let's see, I would do row total times column total divided by my table total. And I bet I can guess the answer. I bet the answer is 21. How did I guess 21? I'm sorry? Yeah, overall, these two, this is expecting what should happen to these 45 kids. Does that make sense? All right. So this one, I would imagine 25.2, but someone should double check that one for me. That would be 70 times 54 over 150. But I would bet it's 25.2. It's up by 1.2 down. So, and then this one, 23.8. Okay. So, do our observed counts match our expected counts? So, now, this is of a sample, so what we have to decide next is, I would never expect, and in fact, I'm going to say there's no way my observed counts could equal my expected counts. Because there's no way I'm getting 28.8 people who completed the assignment. They're discrete, right? These are counts, all right? So we have to be able to decide is the differences between our observed and expecteds, which we can all see are not quite exactly the same, is that difference significant enough for us to say, hey, this assumption of independence is the bad assumption, okay? So to do that, we're going to do a chi-square test on this two-way table. There's two different kinds of chi-square tests on two-way tables. The only difference between them is the name. It is not something that you need to stress out about remembering. I'm going to tell you how you make the distinction. It rarely will cost you much on the AP exam, if at all. I would argue it would give you a 3.5 on a question, which as long as you don't have a second mistake, will still round up to a 4. Okay? At least that's how I grade these. Okay? I got lovely news for you guys. The conditions to do any chi-square test on a two-way table is random, large sample size, independence. Hopefully that feels pretty good. My large sample size is that my expected counts are greater than or equal to 5. The expected counts, right? Okay. Random, you're either going to have random selection, and then your independence will be the 10% condition. Or you're going to have random assignment. And if it's random assignment, you're going to do the individual responses are independent. Okay. The only difference now is your degrees of freedom. Like, I don't want us to look at this table and see 6 different categories. This is not 6 different categories. It just feels that way, but because there's relationships built within them, okay, it's almost like you do the degrees of freedom for each variable and multiply them. Okay? So the degrees of freedom for this is 1. There's 2 categories on this, right? Times 3 categories, degrees of freedom 2. So you're going to do your rows minus 1 times your columns minus 1. Are we good? So in this case, that would be 2 minus 1 times 3 minus 1. Remember, our null hypothesis is our assumption, which is independence. Okay? There are 2 names. There's a chi-square test for homogeneity and a chi-square test for independence. Technically, you run the test the same way. All your calculations, all that kind of stuff, exactly the same. Okay? The difference between them is only in name. It's kind of dumb that they make you choose. But they do. So here's how you choose. Homogeneity is multiple samples from multiple populations or treatment groups. So treatments means if there's treatments, it's immediately homogeneity. So if it's coming from an experiment, immediately homogeneity. Okay? The other things that tend to be definite homogeneity as you're taking samples from different population or from different regions. So different regions are definitely 2 distinct populations. Okay. Otherwise, so if you say it's an experiment or it's regional, that's when I'm going to choose homogeneity. That's a really great rule of thumb. Is everybody good? So for this particular experiment where we're going to run through for this 2-way table, should it be homogeneity or should it be a test for association? It should be homogeneity because it's an experiment. By the way, you guys, test for independence and test for association mean the same thing. Those 2 things, they're identical. Same name to the 2 different names for the same test. Okay? The reason you're going to see me use both, but more likely use chi-square test for association, is I like writing out my hypotheses. There is not an association. There is an association, and then it's done. It's a real quick, easy hypothesis, and that's how I remember it. Okay? So, again, experiments and or regions. And this one is observational studies, typically. All right. All right, so let's pretend we haven't looked at this at all yet. And I just give you, is there convincing evidence of the difference between our treatment groups, okay? All right, so as I'm looking at this one, the first thing I would do, write my hypotheses. And in this case, I would say the proportions of assignment completion are the same across treatment groups. And just in general, I ask that you make one of these two hypotheses in really good, specific kind of like this language. The second one, they are not the same. These hypotheses are never about, like, we're not trying to say what is the proportion of each thing, okay? So we're just trying to decide, are the two variables associated with each other? So you're never going to be like, this one you can't write like PA equals PB equals PC equals, because we're trying to say it's just the same across the groups or not across the groups, okay? And we already said that this should be a chi-square test for homogeneity. I will not mark you down for not knowing how to spell homogeneity appropriately. But can we at least get like the first 5 or 6 letters correct? Okay? But if you get to the geneity part and you don't know how to, that's fine. Are we good? All right, let's go through our conditions. Random. Now, before we do the large sample size and what I need to see from you, I do want to show you some lovely things. Okay, because we are not, and I will not expect for you to calculate each one of these expected values by hand every time in a two-way table. Because I might give you a two-way table that has 8 values in it. Like a 2x4 table is very reasonable. Everybody good? So I want to show you some lovely things in the calculator, because the calculator actually does all of those calculations for you. So we're actually going to run the test before we finish checking in our calculators, before we finish checking our conditions. Is everybody good? So let me pull up my calculator here. And essentially what I need to do, what my calculator needs to know is not just it doesn't just need to know these 6 numbers, right? It needs to know that that these two are in the same column, that the 23 and the 22 go together column-wise, and the 23, the 31, and the 26 go together in the same row. So I need to enter rows and columns into my calculator for my calculator to do this. Now, most of you have been in a course, some of which are enrolled this year, where you put data into rows and columns and thrown it into your calculator. Does anybody remember what that might look like? We're gonna use the matrix menu in our calculator to get there, and our matrix is going to be 2 rows by 3 columns. Okay, it does not need the totals, because right, that's not my real data, those are summaries. It only needs the counts for each cell. Okay, so for those of you who have not worked with matrices before, this part is not that hard, I promise. Okay, so but what you need to do is bring up the matrix menu. Oh no, I forget how to find my matrix menu. Can somebody tell me how I might find my matrix menu in the calculator? All I need to do is stare long enough and I will see the word matrix.
You do alpha F3.
Alpha F3 is quicker? Oh, and you can just do 2 rows, 3 columns? Everybody good? And then I just hit enter. Whew. Oh. Okay, this will be fun. I don't think, we're actually not going to do that. We're actually not going to do that because it'll make sense in a second. So I'm going to get you guys there a slightly different way, okay? So go ahead and pull up that matrix menu and pull up matrix A. Oh, see, I screwed it up again. Go, and when I say pull up matrix A, go to that matrix menu and go over to edit where it says edit. Because what we need to do is we need to store this as a named matrix. Okay? And then up top here, you can change the size and all that kind of stuff. The reason I'm pointing this out is you can change that 2 and that 3 to make it match this. I don't know about you guys, but sometimes I get the 2 backwards. Like what's the difference between 2 by 3 and a 3 by 2? It's like, I know what I'm looking at, but that doesn't mean, Okay, and let's go ahead and just fill in each of these cells here. So I'm going to put 23, 31, 26, 22, Does everybody have the matrix in your calculator? Again, I'm just picking the cells from the table. I have an eel in the back.
Can we work on it?
No, I can do it 7th period, but I got one problem. Okay, here's the next part, guys. Go to your tests. So stat, tests. I'm sure you guys saw this other chi-squared test, right? That we haven't touched yet. Okay. And it says, now, students in the past have confused this, so I want to make sure we're all on the same page. This is saying, where have you put the observed values, and where would you like me to put? This is the calculator talking to you, okay? It's saying, where are the observed, and where would you like me to store the expected? Is everybody good? So when I go through, you'll notice all I really have to do this test in the calculator is put it in a matrix and hit the test. Does everybody see that? Okay, I'm going to go ahead and hit enter. And I am going to write down chi-squared equals I'm going to write my p-value of 0.754. I'm going to write my degrees of freedom. You'll notice that the calculator calculated the degrees of freedom for you. Now, if I go back to that matrix menu and I pull up matrix B and hit enter, you'll notice the exact same expected counts. It rewrote them into matrix B for you. So when I go to check my conditions, so if I were you guys, we're going to run the test, and then we'll go back and backfill the conditions. Is everybody good? In terms of how do you display those expected counts, you can either, it is common practice, and they would accept this on the AP exam. I accept it for sure. If you do exactly like I did up here and write them in the table, that is sufficient. I also have had students who just do this and just draw the matrix for me. As long as your expecteds are written in a way for me to understand, and then you notice that they are greater than 5, that is sufficient. Again, I don't care if you put them in the table versus Yep.
How can we check the independence condition if we're checking for independence?
So what is my independence condition when I have random assignment of treatments? We're just going to say individual students' completion of the assignment is independent. Now, I want to talk about this p-value for a second because we don't normally get p-values in the 0.7 range. Why is this p-value so high? You guys, these aren't far from each other, right? The observed and the expected are pretty close to each other. Everybody good? Okay, so conclusion. We don't have convincing evidence that type of music influences assignment completion. Thoughts? This feels like a good stopping point for today.